Well, my name is Victor Gallego. I'm a postdoc researcher at Comorebi, and I'm also a professor at IE University. And this talk is mostly about how to mix preference models like the Bradley-Terry to other complex models that work with both image and text, okay, deep learning models. So this talk is about how to mix the two to personalize the models to some preference sets, all right? So let's let's start with a motivating example, an illustrative example, okay? So imagine you have some kind of text description of a scene, whatever. I mean, I suppose you are familiar with this because it's like stable diffusion models. So for example, a photo of a dog, okay? And also you have a pair of images. This could be real images or synthetic images, okay? Which are related to this prompt, all right? So the idea is that with a preference model, okay, we can compute a probability of this form, okay? We will define this probability in a few moments, okay? But basically, you can think of this as a ranking model, okay? Between the two photos, which one is the most that you prefer, okay? So the goal is to how we can construct preference models, okay, that deal with pairs of pictures, okay? And we need to construct these preference models, okay, by learning from user preferences, okay? Later we'll see how these data sets appear, right? So I hope that this is a motivating example, okay, because, well, as you can imagine, this is very useful for constructing, building recommender systems, okay? So for a given query, we can return the image that is most liked or the highest quality image, okay, based on a set of candidates, all right? So let's continue, okay? In this setting, okay, there are a few challenges, okay? Which is the first one is that preference data is usually scarce, okay? We usually have limited amounts of preference data because, I mean, preference data is obtained by having users rating lots of images, okay? And one human user cannot rate 1,000 of images, okay? Because that would take too time, okay? So our data sets are usually will be usually small, like 50 images or so, okay? That's one kind of restriction, right? The other challenge, okay, is that to work with image and text, okay? Well, we use deep learning models, but these models are very large. And by large, I mean that they have a very high amount of parameters, okay? So if we combine that these models are over-parameterized with scarce data, okay, we can have problems with overfitting and, you know, right? So that's two important things, okay? And also in this work, okay, well, preference data has like many forms, okay? But in this talk, okay, we assume that preference data comes in a form of pairwise comparisons, okay? So we have a data set of n pair of images, okay? And for each pair of images, one of them is the preferred one, and the other is the discarded one, right? Pretty, I think it's intuitive. Okay, so let's move to the basis, okay? The deep learning models, we need to deal with image and text data first, okay? And then we go to the preference learning part, okay? So, well, this is in order to deal with both image and text data, there is a subfield in machine learning, which is called contrastive learning, okay? That instead of just learning a classifier over a fixed amount of classes, okay, we just process the text with a big neural network, which is called encoder. Oh, sorry. Encoder with some weights θ1, okay, which takes the text, applies some nonlinear transformations, and we get this big T, which is a text embedding, okay, which you need to think of that as a vector, which contains the semantic of the text, okay? And the same for the image, okay? We input the pixels of the image through another encoder with some parameters, and then we get a vector, okay? These two vectors have typically like 500 dimensions, and this vector captures the semantics of the image, all right? So the thing is, if we have a collection of images and a collection of text, okay, we compute the corresponding embedding vectors of the images and the text, and then we can compute the similarities. And to compute the similarities is just the scalar product, the dot product vector, okay? And then we can apply to learn this clip model, which is the most famous one released 2 years ago, okay, it was trained over a lots amount of pairs of image captions from the internet. Okay, so the model learns to associate an image with some text describing the image. Okay, in this way. And why is this useful? Okay, this kind of contrasting models like LEAP are very useful because it allows to build classifiers in which the labels can be specified at inference time. We don't need to train with these particular labels, okay? Because to do this kind of classification, okay, we can just take the text representing a dog and compute the embedding, the text representing cat and compute the embedding, then the text of the embedding of the image, sorry, and then just compute the cross product between all the embeddings and take the one that maximizes the logit, okay? That will be our prediction, all right? This is just the idea behind these contrasting models, okay? You can think of them as some models that take a text representation and image representation, they project to some high dimensional space, and then we compute the dot similarity to see which one is closer, right? Okay, so this is the basis of the deep learning models. And now we turn to preference models, okay, which is the other ingredient we know. So for this talk, we are going to take the Bradley-Terry model because I think is the well-known, the most well-known model released a few years ago, okay. And basically, what this is just an expression, okay, and this model gives that for every assume we have a pair of items, two items like A and G, that can be the images, okay? The Bradley-Terry model estimates the probability of preferring one over the other, okay? And you can see this is a very simple expression, okay? Because we need to just take this S, which is a Latent variable representing the strength or the value of its picture of its item, okay? Then we take the exponential and then we just normalize to get the probability, all right? So if the strength of image E is very high compared to the other image, this probability is gonna be closer to 1, indicating that we prefer image E with high probability. And if these two strengths are the same, this is gonna be like 0.5, which there is no clear preference, all right? So the thing is, we have this very simple model, but it's very useful, right? And our challenge here is how we can use this preference model with preference data in order to adapt the previous contrasting models, okay? Because the thing is, the previous contrasting model has been trained over a lot of millions of image parts from the internet, and maybe that distribution of data doesn't reflect the preference of a particular user, okay? So by combining it with the Bradley-Terry model, we expect to personalize the model to the user preferences, all right? So how can we combine the two models? Well, it's a quite simple approach, okay? Again, I assume we have the text embedding of the text describing the image, okay? And then the two image embeddings, which are subvectors, okay? So the thing is, we are gonna take as the score, as the strength, okay, the similarity score given by the contrasting model, okay, which is, remember that this is just the dot product between the image and its caption, all right? So we just take the similarity score as the strength and just plug it in the Bradley-Terry model equation, okay? So this would be the P1, which is the probability of picking one over the two over the other image, okay? The thing is, if we just take the original contrasting model with this, okay, these probabilities are going to be not very calibrated, okay, because these probabilities are going to reflect the distribution of the training data set of the internet, okay? We need to use this to further adapt it to a concrete set of preference data, right? Okay, so the thing is, we have a probability here. I mean, we can just reorder the preference order. This is just for simplification. And the thing is, I mean, we have a log likelihood here, so we can take this as a loss if we change the sign, right? So this is the thing is this would be just for a pair of examples, okay? But the thing is, of course, if we have n pairs of preference data, as I said like this, we just take this for its for each comparison and then average, okay? That's the usual log likelihood. But the thing is, yeah, instead of the usual log likelihood of a classifier model, we use the Bradley-Terry equation, which is this one, all right? Okay, so, well, while the previous thing works, okay, there is a problem, okay? This clip is a very large model, okay, because it's a deep learning model, so it has millions of parameters, as I said at the beginning. So the thing is doing optimization, the backpropagation rule through the previous laws can be very costly, right, in computing time and also in memory, right? So the thing is, our contribution is that instead of just optimizing all the clip parameters, okay, we are gonna optimize respect the text embedding X. Okay, so this allows to not modify the original clip parameters, the θ1 and θ2, okay, because we just apply a perturbation to the text embedding, okay, and that perturbation is gonna represent the preferences of the particular user, right? And the good thing about this, okay, is that if you do the calculations by hand, it's only a few steps. It's not very complicated, okay? The expression for the gradient of the Bradley-Terry loss with respect to the text prompt is very simple, okay? And we have already all these things because this I1 is the first image, I2 is the second image we are comparing, okay? And P1 is the probability given by the moment at that state, okay? So the thing is we only need to subtract them and multiply, so this is very efficient in time and memory, okay? Because we don't need to modify more parameters, all right? And now with this gradient with respect to X, okay, we can optimize our original prompt X, okay, with just maybe this prompt X is just a picture of a dog, okay, but we perform one step of gradient descent to optimize this loss, and now this X prime, okay, is gonna be the original prompt plus some modification representing the preferences of the user, all right? So that's the intuition between this, okay? You can assume the first part of the gradient is 0.5 at the beginning, okay? So this is making the text description towards the I1. I1 is the preferred image, and far away from I2. I2 is the image we don't like, okay? So it's a way of adapting this with no changing a lot of parameters, okay? Okay, so now we're gonna turn to some experiment and applications, right? Because let's go to a reminder of the introduction. Okay, we have a text description and two candidate images, okay, which are related to that text description, okay? And now we have a model that can compute which of the two images is the preferred one, okay? We have seen how, in the previous slide, how we can learn this from a preference user dataset, okay? So we can, this textual prompt to adapt it to some particular dataset by the user or preference data, all right? Okay, so to continue, now we are gonna, I'm gonna show you two classification experiments, okay? The first one is an experiment in classification, okay? So we take a set of generated images, which is called diffusion DB, is freely available, okay? And the thing is, these images are ranked, okay, and also pairwise ranked, okay, in two sets, okay? For each pair, okay, the preferred one mostly represents high quality images, okay, and the discarded set, the negative set, is low quality images because they have distortions like some blurriness, glitches. I mean, you get the idea, all right? So the thing is, we want to see how well we can learn to this distribution, okay, with the previous fast gradient, okay? So to do this, in this data set, okay, we do the usual thing, okay? We split in training sets and a test set, okay? To analyze the learning, the training set goes from just 1 pair to 50 pairs, and the test set is gonna be 2,000 pairs, okay, of images. And then for each pair of images, once we learn with the training set, we predict over the test set, the pair of candidates, and then we score a match. So the accuracy is 1 if the preferred image matches the ground truth, or 0 otherwise. I think this is the clearest way to define the accuracy in this kind of pairwise dataset setting. Okay. So well, you can see here some examples. Okay, because we have we tried different, as I said, different training set sizes from no training set to 50 pairs of images. We tested different model sizes. Like, as you can see, clip is quite big because the smallest version have 30 million parameters, okay, to the biggest one. And we also compare BT, which is our gradient from a few slides ago, with this positive variant, which just uses positive samples. Okay, so no negative samples. It can learn only from the positive things. Okay, so as you can see, at 20 or 10 training samples, the accuracy already saturates. This is a good thing because it means that with a few amount of data, with little data, we can learn almost 80% of accuracy, which is quite good, okay, for this task. Also, I mean, you can see that the bigger the model, we increase the size, okay. I think this will be seen better here. Okay, this is just the results for a training set size of size 50. Okay, so you can see that for each size of the underlying model, without adapting the model, the accuracy is low. If we adapt the model with positive samples, with the positive images, the accuracy grows in each case. But if we use the Bradley-Terry preference, which is both positive and negative samples, as you have seen, the accuracy is much more better. Okay, and we beat also P-score is a baseline from the literature, okay, from months ago. All right. So well, just to finish, as I'm running out of time, we also experiment with generative models, okay, like Stable Diffusion, which is openly available. These models just follow a diffusion process, okay, to generate an image from random noise, okay, and internally they use clip to match the image with the text, okay. So since they use clip, we were tend to use to match, okay, if we can adapt also the Bradley-Terry model to clip to further guide the generation towards higher quality images, okay, following the previous dataset of preferences. And the answer is kinda yes, okay. Here you can see 4 generations for 2 different textual prompts, okay. You can see the generation from the original clip and our variants with the Bradley-Terry preference. I mean, in the case of the flowers, I think it's pretty clear that the second result with the Bradley-Terry preference is of higher quality because there is no blurriness like in the original clip, so it's more sharp, and that's it. Okay. We also, well, the previous thing can be quite subjective, so we replicate the comparisons with more different prompts and a lot of random shifts. Well, 6 random shifts. Okay. And these generations were evaluated by 2 different persons, evaluators. Okay. So from these 3 methods, they have to choose the best one. Okay. Well, it confirms that if we adapt with preference data, and in this case, the preference data is towards high quality images, the images are more preferred most of the time. Okay, because the win rate is the higher of the 3 variants. All right. So just to sum up, okay, further work, I'm working of extending to more general preference models, okay, like the Plackett-Lewis model, which can account for more than 2 preference levels. Okay, this is the probability, which is, as you can see, it consists of smaller parts of the Bradley-Terry model, but imposing the order with the multiplication. So it's straightforward to adapt, but the tricky part is getting a dataset like this, as you can see. Another part is, since we are using gradient descent, we can instead use some kind of stochastic gradient Markov-Chain Monte Carlo to explore the distribution and get uncertainty estimates of this probability and so far. And just to conclude, that's pretty much it. We have seen an efficient method of combining a image text model with the Bradley-Terry preference model that uses little data and has like several good results. Okay. And well, if you're interested, okay, the paper is on arXiv. Okay, it's under review, but I mean, you can have a look at it and ask me any questions. And yeah, I think that's pretty much it. Thank you very much for your attention.
Thank you very much, Victor, for this very interesting presentation. So I open the floor to questions. So I suggest you raise your hand if you have a question. So I'm starting with Andre.
Perfect.
Okay, thank you. My questions or suggestion. So you use Bradley theory and then generalization you mentioned to Plackett-Luce, and I see that Professor Perman, yesterday's keynote speaker, also joined us, who works in probability. There was a very interesting lecture at the recent Stochastic Processes SPA conference in Lisbon by Percy Diaconis, legendary probabilist, who mentioned Zetlin library stochastic processes which extend, they nest both Bradley theory and Plackett-Luce, and perhaps they could be used in this case for the recommender systems to extend things further. They are based on ranking of books, but they nest all sorts of those families. Maybe they could be used to extend this model even further. It's Zetlin library, but many things are open here, possibly to be used for this case.
Thank you for your comment, Andre. I believe I was looking for like different preference models, but what you have suggested based on stochastic process can be very interesting, because maybe you can adapt it a long time and change dynamically a long time of a stochastic process or so like that. That will be useful in recommender system, because maybe the preference of the user changes a long time, so it's natural to try to use all of that. So it's a thank you very much.
Thank you. Thanks.
Zikicha?
Yes, thank you. Thank you for the great talk. I'm by no means the expert in the field. I have just a short question. You mentioned earlier that you have used 2 independent human experts to verify the quality. My question is, what happens when their opinions collide? And is this the standard in the area? So let's say human expert 1 says X is better, human expert 2 says Y is better. What do you decide in that situation? Thank you very much.
Okay, thank you. That's an interesting question. Well, in this case, if there is a disagreement, it doesn't matter, because globally we take the win rate. So it's maybe one model wins per one evaluator, another model wins per evaluator, and that takes in a global count and then average. Okay, but yeah, I think a good thing to do, which I didn't do yet, is to, since we have 2 evaluators, we can compute some kind of inter-evaluator agreement or some quantity like that. So that, yeah, maybe the thing that will happen if the inter-evaluator agreement is high, okay, no problem. But if the inter-evaluator agreement is low, I think, yeah, I mean, maybe add more evaluators or try to define the task better, right? Because here, I mean, the task was defined as, okay, which of these 2 matches, which of these, or three outputs, because we are comparing 3, which of these 3 is of higher quality? And by higher quality means no blurriness, high definition, you get the idea. But maybe if the inter-agreement, inter-evaluator alignment is low, I think, yeah, one solution would be to add more evaluators or to further define more narrow how do they evaluate, right? Because there is some amount of subjectivity here. Yes, that's true.
Are there any other questions? So I have maybe a few questions myself. First question is in terms of CPU time. So you say it's not too demanding, but I was wondering what extra time you need compared to these 2 others. So
yeah, I think the extra time is just computing. Okay, you have the 2 embeddings already computed. The extra time comes from this P1, which is the computing the similarity, which is a matrix multiplication, and then the softmax function.
Okay.
So it's I mean, it's not very much, but I mean, it's a little overhead, but I mean, the
Yes,
thing is
sure.
that you don't need to compute the gradient because you can compute it by hand, so you avoid having to do backpropagation, and it's kind of cheap. Yeah.
My other question is maybe stupid. It's a bit a clarification question about the evaluator. So I got the question, hearing the question from Zikicha. So you want the image to represent the preference of the specific user. So how does this work? So you have these evaluators. They first give opinions about several images. Then you feed that to your BT model, and then they evaluate the output of the 3 models.
Yeah.
Okay, so that okay, great.
Yeah, I mean, of course, if this is a fine-grained personalization, that is not possible because each evaluator would have his own taste. Okay, here to make some kind of objectiveness, okay, the preference is defined as, okay, you prefer images of which are of high quality with no defects, okay, to make it more objective. Okay.
Oh, okay, I get it. Yeah. Okay, get it. And yeah, maybe a final. It's again a quite clarification question. So you talked about the accuracy metric, and I understand, of course, that the closer you are to 1, the best it is. But what does this measure precisely?
Oh, it's a so I think so. It measures that, okay, you are given 2 images as a test set, and if the fine tune in the tuned model gives a prediction, okay, it's 1 is the best or 2 is the best. Okay, so the accuracy measures if that is a match, respect the ground truth in the dataset.
Okay, so it's just 0, 1, and then it's average. So yeah, okay.
Yeah, I mean, we can only 0, 1 because we don't have the underlying probability.
Yeah, sure.
So yeah, it's but yeah, I don't know, maybe. Yeah, an important thing, okay, this is just a classification experiment, okay? I didn't have time, but okay, I also did retrieval experiments, and in that case, I not use the accuracy, I use the retrieval metrics like precision at some level or recall, okay, and see if the recall achieves a better that. But yeah, it's